The bundle line, I think.
Okay, and so you would imagine putting those...
I think it's required on left hand. Some of the optics automatically does on left hand. But you don't know whether you're 100% identical. That can be a structure test in higher order.
Any other questions or comments?
Thank you again. The next talk is by Wadikima from MIT on the landscape of intersecting brain models.
Thank you. Okay, I'd like to start by thanking the organizers for organizing this wonderful conference. So I want to report on some work on trying to compute probabilities for different vacua. And I should start by mentioning my collaborators, Ben Feifel, who is a postdoc at Berkeley, Matt Lippard, my student, Yisheng Yang, and Ronnie Harnick, Graham Chris, Gillette Perez, and Massimo Ferrari. So the goal, the motivation here is to walk the long path from perdition via atonement to redemption. And I'll have nothing to say about step one. I'll leave that to the many other experts who are here and yet more who are not here. The first step being surveying the string theory landscape. I think we're only scratched the surface probably of understanding what kind of vacua, especially non-symmetric vacua there are, and what kind of properties they have and how those are statistically distributed. What I'm going to focus on are the other two steps that are assumed by many to be involved in arriving at predictions. One is to take this input from theory state and churn it through the machinery of eternal inflation. They preferentially populate some vacua over others. And there's a potential for an enormous rebalancing of probabilities when that happens, because the way we usually think about inflation, there are exponentially large expansion factors involved. So I'll argue that those are actually less important than we might have thought. And then finally, after we've produced all these vacua in different parts of the universe, that's still not the answer, because of course in most of them there won't be any observers. And so I'll try to say something about how we might try to select for vacua in which there are observers in a situation where everything scans and it becomes very, very difficult to write down specific conditions for observers. It's hard enough to do it in our vacuum, but what if we have completely different low energy theories? And so the new part of the approach that I'm going to present can be sort of summarized in these two words here. I'm going to try to move away from a lot of the ambiguities and pathologies that one finds in trying to define probabilities in eternal inflation by focusing on one causally connected region, the kind of approach that's motivated by the holographic properties of black holes. And as far as anthropic selection goes, I'll try to argue that at least at the crude level, we can replace these very prior-dependent criteria by a new criterion which I'm going to call the anthropic principle. In fact, I should give my collaborator, Ronnie Harnick, full credit for the horrible pun. Okay. So let me start with point number two. As I said, I have nothing to say about point number one. And let me just quickly review why it is so hard to get sensible probabilities out of eternal inflation. So this is the idea of how the potentialities of the string theory landscape are turned into actual bubble universes that are distributed throughout some global, eternally inflating universe. These different colors indicate different vacua, and they're bubbles that nucleate inside other bubbles. You sort of by these tunneling processes that allow you to jump from one local minimum in the landscape to another, and eventually work your way through the landscape and populate all these different vacua as actual regions in the universe. And now you'd like to make a statement along the lines of, we're populating a lot of green vacua, or the green vacua have a huge volume, and so somehow the green vacua are the most likely. I don't know if this is actually what it looks like in this picture, but anyway, those are the kind of statements you're after. And they're hard to make, because first of all, there is a natural slicing within each bubble. There are natural three-dimensional space-like surfaces of constant energy density, and those are open. They're hyperbolic slices. One can show this. This follows from the symmetries of the instanton that forms the bubble. And so each bubble is infinite according to the natural slicing that would be used inside the bubble. So an infinite open FRW universe. And so that immediately makes it difficult to compare volumes. Okay. Each one of these bubbles is infinite. And then, of course, in this process, we're actually inflating an infinite number of red bubbles, an infinite number of green bubbles, and so on. And so there are multiple levels of infinities that call for some sort of regulator if you wanted to make a statement about red being more probable than blue or something like that. Okay. And so, let's see. So let me come up with a regulator here. So can everybody read the stuff that's down here? That's what I tried to. So one idea for a regulator is to look at finite time. Okay, so what I've drawn here in purple is a finite time slice, and at this time the universe in its totality is finite in size. Okay, and so we could, what could we do? We could compare the total number of green bubbles or red bubbles or blue bubbles that this slice cuts through. That's one thing. Or we could look at the volume. We add up all the volume of the green bubbles and the volume in red and the volume that's blue. Which of these are we supposed to do? And of course, interpolations between these two extreme possibilities. Okay. And there are indeed probability measures that were proposed that are basically based on those different kinds of weightings, by volume or by number. And interestingly, they have a lot of the same authors on them. I mean, it's really confusing. They give different answers. Well, obviously. Okay. And I don't mean to sound extremely critical. I mean, Vilenkin and his collaborators have really been, out in the desert alone for many years trying to tackle this extremely hard problem that's sort of been around ever since it was recognized by basically Guth and Weinberg that inflation is generically eternal. Okay. Well, suppose we agreed on one of these two possibilities, then we still have another problem, which is, at which time are we supposed to count the bubbles or measure their volume? Okay. I told you that there's a preferred slicing within each bubble, but there is absolutely nothing that tells you that this line is worse or better than the straight purple line that I drew. The universe is extremely inhomogeneous on scales larger than the bubbles, and there is just nothing that picks out a particular slicing. And as you can convince yourself, you can get any answer you want by choosing a suitable time coordinate. In this case, I've carefully avoided all the blue bubbles. The probability has suddenly gone to zero. Okay. This was, in fact, this problem was recognized very early by Andraminda and his collaborators. Now, my take on where these topologies are coming from is somewhat influenced, as I'll mention in another transparency, by our experience with black holes. That what's pretty clear is that it's the global or bird's eye view of this geometry that is a precondition for running into all these ambiguities and infinities. And what we also know is that this global bird's eye view is a theoretician's fantasy. It's not what anyone can actually see, and that follows immediately from causality. Imagine that you're an observer following this low line. Well, the causally connected region that you can access is basically what I've shaded here in purple. And it doesn't include almost everything here in this universe. In particular, for any one observer, a generic low line that you just pick, inflation is not eternal. You eventually run into some bubble where it can end. It's only in the global picture that you can always find some places where the universe is still expanding exponentially, and because it's exponentially fast, the bubbles before never quite catch up with it. But for any one observer, inflation ends, and volumes are finite. And so maybe it's worth exploring a description of eternal inflation that's centered on one observer. It has to be any one observer. We obviously don't want to say, okay, you can only describe a guy who happens to be going through a green bubble and then a red one and then a blue one. But we don't want to make reference to the fictitious global picture that no one can actually see. Okay. And so the region that one observer can see is called the causal diamond, because this is the world line, and this is the future light cone from early time on the world line, and this is the past light cone going down from a late time, and whatever is in here can be directly probed and accessed, and anything that's outside cannot. Okay. So what I'm looking for is a description that makes reference only to this type of region, something that can fit inside such a diamond. Now, one additional motivation for this is simply to try to be economic. Why should we try to work so hard to describe all these things that correspond to no actual experiment anybody can do? But another is a lesson in the context of black holes that we actually get burned if we try to do this. At least if you believe, as you should by now, that black hole evaporation is unitary, you run into the parent paradox. So here's Hawking radiation coming out, carrying the state psi that was the quantum state of the star that made a black hole. And you're inside the black hole on the same space-like slice as that quantum state. The star just at a later time. So it looks like if there really is that information in the Hawking radiation coming out and telling you what went into the black hole, that you Xerox the quantum state psi. And that violates linearity of quantum mechanics. And the way that we think we get around this apparent paradox is to notice that it's again an artifact of this global point of view. Here, just as in eternal inflation, nobody can actually see both of the copies. And so if you're happy to just describe what any one observer can see, there's never an explicit contradiction. Okay. In a sense, eternal inflation is actually worse. If you do focus on one observer, let's say here outside the black hole and here in eternal inflation, there's a difference. The guy outside the black hole, if they know what the initial configuration is, can at least predict the gross features. Which I'll emphasize this also today in this talk. Holography is something that's very supplement about quantum states. You can still predict the gross features of the metric in here, for example. There's no ambiguity. You can still define effectively at least a semi-classical metric that is really global. But in eternal inflation, you can't even do that. Because gross features of the metric outside your horizon depend on the outcome of quantum fluctuations that you never have any chance to see or that don't decohere for you. Okay. So there are all these bubbles that could potentially change the cosmological constant to different values, change the curvature, that could form in all sorts of places here. You have no idea where. So there's no good semi-classical geometric description of this region. It's a superposition of all these possible geometries.